Alright, hello everyone. So in this first video here, we're going to take a look at the beginning of a conversation of techniques of integration. So the first technique that we're going to discuss is integration by parts. And integration by parts has a couple particular forms of integrals where it's useful, and we'll talk about that briefly. First, what I want to just look at is the derivation of the formula that we're going to use for integration by parts. So if we think about, let's say, the product rule, we have, let's say, f times g, and we're going to take the derivative of that product. So, typically we do this in one of two orders. We say derivative of the first times the second plus first times derivative of the second. So, if we think about at this point, we could integrate both sides of this equation, right? So I could integrate the left-hand side of this equation. I could integrate the right-hand side of this equation. Now, if you keep in mind, the fundamental theorem of calculus says that the derivative of an integral they undo each other. They're inverse operations, if you will. So on the left-hand side, we just get f times g. And then on the right-hand side, we have the integral of f prime times g plus the integral of f times g prime. So usually what we do at this point is we solve for one of those integrals. Now the integral we're going to solve for is the one on the right hand side over here. Right? So we're going to say that the integral of f times g prime is equal to, we're going to have f times g minus the integral of f prime times g. So this is the version of the integration by parts formula that we're going to consider here. And I have a righto over here, right? So we solved for this integral here. So we have f times g prime. Integral of f times g prime equals f times g minus integral of f prime g. Now you'll see some conversations write this in a slightly different manner. And they will write that the integral of u dv equals u times v minus the integral of, this is v right here, and then this is the derivative of the function u. So you will see some situations where they will write the by parts formula in this manner. And the advantage to that version is that it's kind of like a u substitution, right? When you think about we do u substitution, we change the variable, we let u equals x squared, and then we find the du term, which is the derivative of u. So we'll see that similar kind of approach here. So let's take a look at a relatively straightforward example where we're going to use that formula to evaluate the integral. So let's say, as an example, we want to integrate, let's look at x times e to the x. Now, in our strategy of doing integration by parts, one of the things we're going to learn, and again, we'll talk about this more formally in a second, one of the things we're going to learn is that when we have, let's say, a polynomial, which we have here, times an exponential, the best approach is to let u equal that polynomial term. So what I'm going to do is come over here, and I'm going to let u equal that polynomial term. So let me just change color here to kind of keep things a little organized. So we're going to have u equal to the polynomial term. And then what we're going to do is assign dv to the other term in that integral. Right? So if we look at, up here, if we look at this form of the integral, the product that we have in our integral, one of the terms we assign as u and one of the terms we assign as dv. Right? So then what we're going to do in our formula, right, we need the du term. So we're going to take the derivative of the u. Right? Now keep in mind, notationally, u is a function of x. So we're going to take the derivative of u with respect to x, but in our formula what we want really is just the du term. So I'm going to solve for du. And then over here, we're going to integrate. So we have the dv term in our integral. We need the v expression in our formula here. So we're going to go ahead and integrate. And, you know, the integral of dv will equal the integral of e to the x dx. Right? So when I integrate a derivative, I get the original function. And in this case, the integral of e to the x is e to the x. And remember, you know, normally when I would integrate a function, I get a plus c here. But what we're going to do basically is ignore the plus c. Or a better way to think about it is this is true for any value of c. So what we're going to do is we're going to choose c equal to 0. And we're going to say this is true if c is 0. So we're going to come back to our formula. All right, so I'm going to rewrite the formula. Here was my formula that we have here. So our formula says if we have the integral of u times dv, that's equal to u times v minus the integral of v times du. So I'm going to plug in this stuff that we just worked out. So the integral of x e to the x that we wrote, we are going to take u times v. So my u is x. And my v is e to the x. And then I'm going to subtract the integral of v. So my v, again, is e to the x. And then in this case, the du is just equal to dx. So there's my, let's say, converted version. Right? So I'm converting kind of like a backwards power rule, right? This is the power rule that we manipulated by integrating both sides. So right here's an integral version. So we've taken the integral that we've had and we've converted using our by parts formula. Now, one thing that we should notice when we use this technique, and here's the advantage of this technique, this secondary integral should get what I'm going to call simpler, right, or cleaner. So if you look at the original integral, it was a polynomial times an exponential, and now it's just the exponential, and we can evaluate the exponential. We know how to evaluate the integral of e to the x. So that secondary integral is getting cleaner or easier. And in this case, it was just the integral of e to the x, which we know is e to the x. And then we'll go ahead and tack on our constant there. So we're going to say here's our final answer. We're going to say the integral of x e to the x is x e to the x minus e to the x plus c. So there's a quick illustration of how by parts works. And what I'm going to do is talk about the strategy that we're going to use here when we do integration by parts. Right? So there's a couple different mnemonics for remembering this. One of the mnemonics is we're going to say LIATE. So LIATE, L-I-A-T-E. So this is, in essence, the order of preference for my u term. Right? This gives me the order of preference for choosing the u term. All right. So here's what you know, this represents. Right. So the L represents logarithmic. So if I have a logarithm in my integral, I'm going to let u equal that logarithm. That's the best approach. If I have an inverse trig function, right, then I'm going to choose that as my u term. Right? Now, if my integral involves a logarithm and an inverse trig function, obviously I'm going to choose the logarithm. That takes precedence over anything else. And then A means algebraic. Right? So what that really means is polynomial. Right? So if I have a polynomial, like we had x to the first, that's an algebraic function. All right. So you know that's polynomial is what we typically mean there. T represents trigonometric. And then E represents exponential. Oops. E represents exponential. Okay. So those would be the preferences that I take upon choosing the U term. I can't spell today. All right, so exponential is what we're looking at here. Okay. So in our example, we had a scenario where we had a polynomial times an exponential. So we have an algebraic times an exponential, and if we move down our order of preference, we can see algebraic comes before exponential. So that is why I chose the u to be the x term. So let's do a couple more examples where we will see that in action. So let's take a look at an example like this. So let's say we have x times ln of x. Right. Let's take a look at something like that. So let's write out the integral of x times ln of x dx. Right? So if we follow our LIATE process, we're going to let u equal the logarithm, because that was before the algebraic option, and then we're going to let dv be the algebraic option. Okay? So then we're going to differentiate the u. And again, I'm going to get a little lazy here. Instead of writing du over dx and then multiplying the dx to the other side, I'm just going to write the dx on the other side. And then instead of writing an integral on both sides here, I'm just going to mentally think I integrate. So I integrate dv to get v. I integrate x to get 1/2 x squared. So again, remember our formula is the integral of u times dv equals u times v minus the integral of v times du. So our integral again is x times ln of x. And for this particular problem, right, we let u be the ln term that took preference. So I get ln x times 1/2 x squared. And then the integral of v du. So v was 1/2 x squared, and the du expression is 1/x. All right, now if we clean this up, right, I'm going to focus on that for just a second. If we clean that up, let's pull the 1/2 outside the integral. And then x squared over x is going to reduce to just x. Right? So I'm going to simplify that expression, and x squared times 1/x reduces to just x. So again, here's the advantage of by parts and what should happen. We had a product of a algebraic times a logarithm, and this integral in our formula has become quite simpler. So we can integrate x really simply. That's 1/2 x squared. So here's, again, a visualization, right, an example where we see that secondary integral getting simpler. Right? So I'll point out to you that if the second integral does not get simpler, then one of two things is happening, right? One of the errors might be that I chose u to be the wrong term, right? I didn't follow the LIATE process. And then the other issue might be, well, by parts just doesn't work on this integral form. And we'll talk about in a couple minutes forms in which by parts typically works, right, and forms in which it doesn't. Right? So we have 4 techniques of integration we learn about in a particular chapter of this nature in a calculus textbook. And by parts is the first one. By parts doesn't always work. And by the end of the conversation for the 4 techniques of integration, we'll be able to have kind of a conversation about strategy and when by parts will work or when by parts won't work, and we would try one of the other techniques of integration in those cases. All right, so I want to show you something pretty cool that if you have a TI calculator where we could kind of check our answer for the integrals we're doing. So first of all, I just want to remind you that you should be able to check your answer pretty easily. You know what? I didn't finish this problem. Let me finish this problem real quick. So we have the integral of x ln of x dx. That's going to equal 1/2 x squared ln of x, and then minus we have this 1/2. And then we're going to get out of this integral 1/2 x squared, and then we'll say plus c. Right? And obviously I could write this as 1/4 to be my final answer. All right, and I was getting a little excited about the calculator, so I'm going to take a second and show you how we could use the calculator to check our work here. So to check my work, what I could do is the following. So let's say in Y1, I'm going to type in my answer. Right? So in my answer, I had, what do I have? 1/2, so I'm going to do 0.5 x squared, and then times ln of x. Wait, I don't think that's right. Let me double check. It is right. So we got 1/2 x squared times ln x, and then we have minus 1/4 x squared. So we got 1/2 x squared ln x, and then minus, I could use fractions, even though 1/4 is 0.25, right? So let's say 1/4 x squared. So this is going to be my antiderivative, right? And then I'm going to have the calculator evaluate the antiderivative. So where that's located is under math, and then I'm going to choose 9. And that's the function integrator. So what I'm going to do here is I'm going to integrate from 0 to x. I'm going to leave my upper limit of integration an arbitrary variable. All right. So what that's going to do for me then is it's going to allow me to integrate that expression in terms of x. Right. So remember, when we have a definite interval of integration, if I'm going from 0 to 5, when I integrate, that's going to give me a numerical value. So I don't want to go 0 to 5, I want to go 0 to x so that I get an expression of x for the antiderivative. Right? So what I was integrating was x times ln of x. So there's the function, right? My integrand, right? And then I'm going to evaluate that at x, right? So there's the calculator's antiderivative. Now what I could do is I could graph, but I'll be honest with you, the graph takes forever, right? So here's the graph of the calculator's version of the antiderivative. Well, that was my version. Sorry, the blue one graphed really quick. And then the red one's the calculator's version. And look how slow that's going. Right? I don't really want to wait for that, so I'm going to do second off, second on, and I'm going to stop that. Let me go ahead and clear, and then I'm going to go to the table, so I'm going to do second graph and go to the table. And when I go to the table, what that's going to do is allow me to look at and compare the two expressions numerically. So I can see when I look at the table, y1 was my version of the antiderivative, and then y2 was the calculator's version, and we can see numerically they're identical to each other. Right, so that's checking our work. Right? So which is pretty cool to be able to use technology to do that, right? And then again, obviously, what I could do is I could come back to my answer down here, and I could take the derivative of the right-hand side, and that should take me back to my integrand. All right. So I could check analytically, or I could check graphically. All right, so let's take a look at one more example, and I want to consider a word problem here. So in this word problem, we are told that a particle moves along a straight line and has a velocity v of t equals t squared e to the negative t meters per second after t seconds. So the question is, how far will it travel during the first t seconds? Now, if we remember what we learned in a Calc 1 course, probably, is that we have a relationship that if we have position, right, the derivative of position is equal to velocity. Right? So we're being asked, like, how far did it travel? We're being asked a position. So to find position, right, we're going to integrate both sides of our relationship here. And when we integrate both sides of a relationship, we're going to get the integral of a derivative are inverse processes. So position is found from integrating velocity. Right? So to find our position here, we're going to integrate our velocity function. And therefore, what we are integrating in this case is t squared e to the negative t dt. Now, when we look at this, notice that we have a product of a polynomial, an algebraic term, t squared, and an exponential, e to the negative t. And if we go back to our LIATE, if we look at LIATE, right, LIATE says that we're going to look at logarithms first, Then we're going to look at inverse trig functions. Then we're going to look at algebraic. So we have an algebraic, t squared, right? That's going to be our u term. And then we have trig and exponential, right? So the algebraic trumps the trig or the exponential. It chooses higher preference, right? So I'm going to let u equal the algebraic term, and then I'm going to let dv be e to the negative t dt. So then I'm going to differentiate. Du will be 2t dt, and then I'm going to integrate here. So v will be negative e to the negative t. Right now, I want to keep in mind, usually in a prior chapter, you learn about doing u sub here. You would let u equal negative t, and you would get a negative du. And that's where this negative comes from. Now, ultimately, we don't want to have to do u sub within our by parts problem, right? So, there's a couple concepts to remember. One of them being that if I have the integral of e to the linear expression, if I have the integral of e to a linear expression, I'm going to write that as ax plus b, right? Then that antiderivative is always going to be 1 over a e to the ax plus b. So I don't want to have to do a u sub for that problem, right? And then ditto, one other example to keep in mind, if I'm integrating a trig function, right? Let's say I'm integrating cosine of ax plus b. Right? So the antiderivative of cosine is sine ax plus b inside there, and then I'd have a 1 over a. So if I did the u sub for ax plus b, I'm going to end up with the du being a dx, and then I get a 1 over a in my antiderivative, and same for the exponential. So I want to memorize those. I want those to be common knowledge, and I don't want to have to be doing u sub on those problems. So back to our problem we're looking at. So we have, again, the integral of u dv is going to be u times v minus the integral of v du. So we're going to plug in what we have here. So we have the integral of our t squared e to the negative t dt. It's going to equal u times v. So we're going to have t squared negative e to the negative t. So I'm going to say negative t squared e to the negative t, and then I have minus the integral of v du. So my v is negative e to the negative t, and then my du is 2t dt. Right. Now remember I said earlier that the secondary integral should be getting simpler, and it actually is. Right. Our original form of our integral was a quadratic polynomial. The secondary integral here is now a linear algebraic, so it is getting simpler. So let's go ahead in that second integral and let's clean that up just a little bit, right? So remember, it's kind of typical for us to write the algebraic as, let's say, a coefficient of the exponential. That's typically how we write these things. And then I have a 2 and a negative. I'm going to pull those constants out of the integral. So I'm going to get a plus 2, the integral of t e to the negative t dt. Now when I look at the secondary integral, it still has the form of a product of an algebraic times an exponential. So I'm actually going to have to do by parts a second time here. So I'm going to do by parts again. Again, I have an algebraic which takes precedence over e to the negative t when I'm choosing my u term. So I'm going to choose u to be the algebraic. I'm going to choose dv to equal the exponential term. So I'm going to differentiate the u term. The derivative of the derivative of t is 1, and then times dt, and then I'm going to integrate and get negative e to the negative t from my dv term. All right, now I'm going to tend to run out of digital paper here, but bear with me. So I have my original integral equaling all of this stuff here, right? So all of that equals negative t squared e to the negative t, and then I have plus 2 times. Now keep in mind, this formula again is u times v minus the integral of v du. So I'm going to have u times v, which is t, right, negative e to the negative t, minus the integral of v du. So integral of v, and then du is the dt term. So there's my secondary integral of that second integral, right? So I have my second integral I did by parts, and here's that result. Let me go ahead and clean that up a little bit more. So I have negative t squared e to the negative t. That is a sloppy t squared. Right? So I have negative t squared e to the negative t, and then when I distribute the 2, I'm going to have negative 2t e to the negative t, and then I have minus a minus, which is a plus, and the 2 distributes there. So I have 2 times e to the negative t. And then this integral is simpler, right? So again, check this out. We went from a quadratic times an exponential down to a linear times an exponential. And then doing by parts on this again, we've gone to just a constant times an exponential. So we know how to integrate that exponential. And let's go ahead then and finish this problem. So when I evaluate this exponential, I'm going to get just negative e to the negative t. And I'm going to have the 2 times that. Right? So hope you're okay with me going ahead and erasing that negative sign for a second. And then I'm just going to write negative 2 e to the negative t. Right? And then I have the minus 2t e to the negative t. And then I have the negative t squared e to the negative t. So there's my final answer. My final answer, therefore, is right here. So in this scenario, we had to do by parts twice, which is totally okay. That's totally acceptable for me to have to do by parts twice. All right, now I want to remind you here, right, within the context of this word problem, we took a velocity and we integrated to get a position. So here's my position function. And remember, most textbooks will write position with the variable s of t. Right? So I would go ahead and write s of t equals, and what we could do, this is not necessary at all, right? But what we could do is write, go away, right? What we could do is write that s of t equals, and I could factor this exponential out. Totally not necessary to do that, but you might see some textbooks do that or some solution manuals. And actually, you know what I could do? I could factor that negative out as well. Let's go ahead and do that. And then I'm going to have positive t squared plus 2t plus 2 is our result. So there's our final form of our position. All right, so there's some examples of illustrating integration by parts.